Okay, I'm following up on doing the calorimetry related to the palladium-boron. I recently moved to Utah and affiliated with Dixie State University, the newest university in the state of Utah. The Navy started the program in 1992. It came about mainly because of ICCF-21. Quite a few Navy people were there. That was my first report on heat correlated with helium, and Stan Spock, Pam Boss were there, reported on the co-deposition method, and Scott Chubb, Talbot Chubb were there and reported on the lattice-induced nuclear chemistry, their theory, where helium, even though it's produced in the lattice, would appear in the gas phase, which I thought was rather nice. And so the people there, including Bob Nowak and Dave Nagel, and we decided to try to formulate a Navy program. We talked to Fred Sawfield, who was the main person heading Office of Naval Research, and we got a program started in January 1992. The calorimetry I used, it took us a while to even break even. We're usually running negative on less heat out than heat in, but finally we developed this calorimetry after about 4 or 5 months, and we used palladium we had at the lab in China Lake, and we did not get excess heat, and therefore China Lake and my name is in the ERAB DOE report, along with Caltech and MIT, as a group not getting excess power. And because that's what we had for the first 6 months. Well, after 6 months, a lot of other groups had given up and reported nothing, like MIT and Caltech. It takes a long time to look at all the variables, and I knew that. And the main variable we found, you have to have the right palladium. Some palladium, no matter how many times you run the experiment, they're not going to work. And I don't have time to go into calorimetry, but anyway, that's the calorimetry we used at that time. And it was accurate about I would say plus or minus 20 milliwatts. We got a lot better calorimetry later, but once I got excess heat, I didn't want to change things, so I left it the way it was, especially after we had helium. I didn't want to change anything because we wanted to do more helium studies. We wanted to keep everything the same. So we kept it the same for several years. And the Navy program started in 1992, and NRL was making materials like palladium, pure palladium, palladium silver, palladium cerium, but it was very frustrating because nothing produced excess heat. In 2 years, I understand people getting frustrated because that was very frustrating. Sometimes I'd go to other material just to see if I could get the effect still. But in May of 1994, we did get excess heat. The first experiment I tried with palladium-boron, it gave excess heat. And there's some of the points look like they're off. I went back and looked at this point. Well, I changed things around a lot, and on that day, I raised the bath temperature to 50 degrees, so the cell was well over 60, and so I think that's the true effect. I didn't know it at the time, but Fleischmann later told me all their large effects came at cell temperatures above 60 degrees Celsius. He thought that was sort of a threshold to get the larger effects. Should explain some of the low effects too. Some days I would ramp the current up, maybe from 500 milliamps up to almost 1 amp. Well, I found with palladium-boron, when you make a sudden change in current, the excess power often goes away. And not only that, some terms I was leaving out, like the heat carried away by the gases and the work done by the gases. We didn't even know about work. Nobody was using the work term at that time. But those would add to the excess power and bring it up closer to zero. And I should say about calorimetry, almost every time you see things below zero, that's likely a calorimetric error. Very seldom do you see any endothermic process. So just look, see how many times, how the data shows values below 0, and you can consider that probably the error range. I repeated the same palladium-boron a second time, and I've seen this several times. If you do the same experiment using the same material a second time, the second time often performs better than the first time. And this one did. The excess power is higher. This is the 75 weight percent boron that we started off with, and the excess heat is larger. The largest value there is 420 milliwatts in this particular experiment. So it's a good thing to try an experiment a second time. This is another experiment that did not produce excess heat. We could see a flaw in it before we started, so we wondered about it. In the swaging, a large part of the palladium was folded over and made a crack, just like a crack. It almost went the entire length of the palladium rod, the palladium-boron rod. And sort of like we expected, we did not see excess heat in this one. You could argue, actually, that there is some excess heat in that one, but I think it's below the calorimetric error. Now I lost my place where I was, so let me go back. I guess I'm going the wrong direction. But this is where I was right here, and in fact, if you want to look at these view graphs more in detail, they're in a poster, so you can take your time looking at that. But we don't have a lot of time here, so I'm going to skip it. But you could say perhaps maybe there was some excess heat. There's certainly more above the line than there is below the line. So maybe 20 milliwatts average excess power. So whether it's really actually 0, you could argue that maybe it isn't. This was our best result, and Dr. Imam just showed that result. Practically nothing is below the line. You keep forgetting what button to switch here. At least I do. Well, let me go back. I guess it's not working. How do you get it to go back and forth? Maybe I'll let you run it.
This side's go back.
Okay, that goes back. Okay. But it seemed to be responding. Can you get it to respond?
No response.
Is it maybe a battery? Maybe they could go back in the.
Lifted higher than the platform, so it can see the back.
Right, yeah.
No, let's see. Oh, yeah. Going back.
Right.
Where do you want to stop? Here?
Okay, that's where we were. Now, forward is this one right here.
Yeah, right.
So I won't go back. Anyway, this is the best result. This, on the average, it kept sloping upward. It kept getting better as time went on. The reason we stopped it because there was a review meeting back at NRL and Office of Naval Research, and later that day when we had dinner, Bob Nowak, who is manager of the program, told me this may have saved the program temporarily because they were thinking of shutting the program down in 1994. And this did prolong the program, the fact that we had this good result with palladium-boron, because one of the major goals of the Navy program was to make our own material. We knew the key in this field is the material problem. And so we wanted to control over the material and make our own material, and we finally succeeded with palladium-boron. We made our own material, and we were getting excess heat practically every experiment. These are just more results. Nothing really spectacular there, but it definitely is excess heat above the line. Another experiment, not really great, but still above the line. Again, the point up above there, right up there, is again where I raised the bath temperature. So there's reasons for these little spikes upward, is things that I did, like increase the bath temperature, which made the cell temperature above 60 degrees Celsius. In another experiment, almost every experiment, but this is the lower weight percent. This is 0.25 weight percent. And the ones I showed previously, some of those were 0.50 weight percent. We started off with 0.75 weight percent. Now, you might not think that's very much boron, but if you do a calculation, 0.75 weight percent boron is not a very heavy atom. And if you do it by atom percent, you find out at 0.75 weight percent, there is one boron atom for every 15 palladium atoms. So on an atom to atom ratio, it is a fairly significant amount of boron. This experiment started off looking good. You see early excess power, and then it went away. And I have no explanation for that. I went back and looked at it in my report, and I didn't write any explanation for it, and I don't remember any reason. It just stopped working, and sometimes that does happen. Now this is a summary, starting off with the higher weight percents, going to the middle weight percents, going down to 0.25 weight percents, and you could maybe try to see a trend, but I don't see enough of a trend to really make any statement. But I would say in general that the 0.75 weight percent is probably better, and 0.5 is pretty good too. But if anything, I'd say keep it around 0.5 weight percent or 0.75 weight percent. But 0.25 weight percent still gives you an effect. Now, the program did end in China Lake in June of 1995, and it was very frustrating because I put a lot of time and a lot of weekends working on this, and then suddenly the program is over. And that led to problems I had at China Lake, because I think people at China Lake did not really like me working on this topic. A lot of people think it hurts their reputation as an institution. And so I had a payoff when I didn't have any more funding. So, but the good side of that is I probably would never have gone to Japan if it weren't for the way things were things that are happening at China Lake. So when I got a chance to go to NHE in Japan, I went there in October 1997, and I remained there until end of March 1998. In the last 2 weeks there, I saw them tearing everything apart in the laboratory, putting it in boxes, and that was a sad sight too, to see this a really nice cold fusion laboratory being dismantled. And I don't know what they did with all the pieces, but it became more or less an empty room in a matter of a couple of weeks. But anyway, in Japan, I used the Fleischmann-Pons-Dewar calorimetry, a totally different type of calorimetry, because that's what they already had there, because Fleischmann-Pons had tried to help them in this field. And I took a palladium-boron sample with me. It turns out one I've never run before, so this is the first time I ran that palladium. And while I was there, I had to write a final report, and this is my final report. If you see the peaks here and here, that's my final report. And the next slide, when I gave the data to Martin Fleischmann, and that's another story, they told me I could have the data when I left, and they didn't give it to me. But Mr. Sumi, he was one I worked closely with, he later sent it to me by email, and it just page after page of data, but somehow it all came through. So I gave this data to several people. Mike Mealy, I gave it to Martin Fleischmann, and so this data should still be around somewhere. But Martin did this analysis of the same data. This is my analysis, and just look at Martin's analysis. You see the same peaks. Martin's is definitely better. He did it more accurately. He got the cell constant more accurate and a higher one than I was using. And he got the correct heat capacity term. I used 490, which is what they told me, and I didn't measure it separately. And actually, it's more. The heat capacity term is 450 joules per degree, not 490 joules per degree. But the same features are there, and this is the excess power shown by Martin. And Martin was quite upset by this one negative point. He didn't believe it should ever be negative. That's acting like a refrigerator. That's violating thermodynamics. So he wondered whether we ought to change the cell constant. Well, he determined the cell constant to 5 significant figures. And I didn't think it would be very wise to try to change that. So I tried to argue against it. And finally I came up with, there's a work term that we were not using. The evolving gases push against the atmosphere and do work. And you need to consider that term unless you incorporate it into the calibration constant. But if you change the cell temperature, that term changes a lot, and your calibrations will be wrong. And so if I put the work term in, and it's based on the ideal gas law, and the PW is equal to minus RT 0.75 IF, I could explain the 0.75, but it takes time. If you base this reaction on 1 Faraday, then you produce, for 1 Faraday, you produce 0.75 moles of D2 and O2, what it amounts to. And if you put that work term in, on this day 61, instead of a minus 5.2 milliwatts, you have to add 22.3. That's the work term. That is energy carried away, the energy done by the system that needs to be added to the excess power. And so really he had 17.1 milliwatts on that day. It still was low because, like I said, if you suddenly increase the current, I'd increase the current to 1 amp. And often in palladium-boron, for some reason, you suddenly boost the current up, the excess power temporarily goes away for 1 day. But then it came back the next day and it was even larger. So sometimes you have to consider the work term unless you calibrate it into your constant and don't change your current and keep your cell temperature about the same. Then you could get away with it. This is Morton's analysis. This is the excess power and time. For 8 hours, the cell is running. In 6 hours, there's a heat pulse. Morton didn't like that. He said this should have been a 2-day cycle, not a 1-day cycle. The heat pulse should have been for 12 hours, so everything could come to sort of a more or less closer to the total relaxation, to the temperature change. But there is early excess power, positive feedback after the temperature going up. The excess heat starts up, and it's right here. You see, this is the heat pulse, 0.25 watts. It's almost exactly up here to where it starts. Almost another 0.25 where it comes down here, but then the excess power lingers on. So 3rd day, there's definitely a sign of excess power. And it actually comes earlier than that if you look at this graph, but Martin doesn't make his graphs easy to follow, and the numbers are not easy to read. But this is the heat of loading right up here. This is the heat of loading. This is the maximum loading you should have gotten. You shouldn't have gotten any more than this based on the enthalpy of loading. But right off the start, you have excess heat due to something more than you would expect from loading, and then gradually it goes away and almost to zero. Then excess power starts to kick up, real excess power, and so this can start very early. The excess power can start very early. Why is a good question, and I don't know the answer to it exactly, but you can, before we get to that answer, let me go to this. At China Lake, we did eventually get an improved calorimeter. Kendall Johnson was a postdoc, and he spent a whole year working on this. But he got the calorimetry where you could rate measure to almost a milliwatt. And this is not palladium-boron, but this is palladium. And if you turn on the current, you start the loading. And this is the loading right here. If you integrate under that curve, you get the heat of the loading. And we got, my analysis gives you minus 38 kilojoules per mole of deuterium. Now this number depends on what you're relating it to. Moles of deuterium, not moles of palladium, because that'll give you a different answer, a different number. They're both right, but they're different. And the literature value, if you base it on moles of deuterium up to 0.6 loading, the correct answer in the literature is minus 35.1 kilojoules per mole, and we're within the error limit of that experiment. I just want to show you that eventually we got much better calorimetry, but that was in 1995, and the program didn't last very long. We only got a couple of studies with that calorimetry. but I want to show what loading looks like. Now, in 1995, in January, I went back to NRL trying to help them get excess power because that was the thing blocking the Navy program. They had never found any sign of excess heat, and there's another reason for that, and I could go into it, but they changed my calorimetry so the air was plus or minus 250 milliwatts. Well, that makes a big difference, because most of my effects would be in the air range, if that were the air. But they've just gotten a new Seebeck calorimetry, which is very good, apparently. And you see when they started the experiment, there is excess heat due to loading. Well, I calculated that under the curve, integrating under the curve, and I gave it minus 33, plus or minus 3. So it does give you the, Palladium-Boron gives you about the same loading as enthalpy effect as palladium. But I had to go back to China Lake, and I didn't really see how they designed everything at the end, but they had the gas exit lines going horizontal. Well, the gas exit lines are carrying water vapor, heavy water vapor. If they're horizontal, that's going to condense at lower temperature, at the room temperature, and so they get clogged. They don't clog right away, but as you go on, they get clogged, and then pressure builds up and released, and builds up and released, and so you get this noise. But it lasted for 40 hours, and enough to get you see the effect of loading. And this even stayed higher than it really should be right here. It's still above 0. And if you go to another cell, they ran 2 cells simultaneously. If you go to this other cell, you see the loading, but it doesn't go away. Even when it should have been completely loaded, the excess power continues. And it even goes up higher than you'd expect from loading and continues on. And they even boosted the current up. It's still fairly kind of low current, but then they got excess power up to here to 15 milliwatts. And then the gas clogging of the lines sets in, and you have that. But I didn't see this until Steve Cribbett sent it to me a year ago. And I wish I'd seen it earlier, because this, to me, is proof that NRL did get excess power with Palladium-Boron, but they did not recognize it because of the air with the lines getting clogged. So I wish some things we could do over. But anyway, going on, I ran another experiment last year in my kitchen in Ridgecrest before I moved to Utah. We had 2 homes. My wife was in Bakersfield, so I had the whole house, and I used the sink right next to the kitchen. Well, I measured data right from the very start, every minute or every 2 minutes, because I was trying to test Fleischmann's equations that predict initially the cell temperature will go up in a linear fashion. It'll increase linearly with time, and it did for about 10 or 15 minutes. But just about a week ago, I said, maybe I should go back and look at that data for excess power, which I did, and I haven't had enough time to really think about it, but go back. But anyway, I'll just go into this, but at first when I saw that early excess power, it appears that the first minute, the first data point I took, there is excess power. Well, the first thought I had was maybe the nuclear active environment or the reaction zone is already present, and all it needs is deuterium injected by electrochemistry. That would be a nice answer, but then more thinking, I don't think that's the answer. And still, I've thought about it more while I'm here. And what I think now that happens, I think boron under the electrochemistry and the high pressure of deuterium going into palladium, I think boron may be reacting with the deuterium and forming boron deuterhydrides. Or you look in the literature, there's BH, there's BH2, there's B2H6. And what that would do, that would change the thermoneutral potential, because that assumes that you're only doing water electrolysis. If you're doing something else as well, that will be a different thermoneutral potential, and that could explain, I think, the excess power we see right at the beginning. But I still like the idea maybe active sites are already there and they just need the deuterium to be sent in by the electrochemistry. But that's nice, but it's probably not true. So anyway, this is a summary. The Palladium-Boron Cathodes made by Dr. Imam at NRL that I've ran, they gave excess heat in 9 out of 10 experiments, and you might even say 10 out of 10, because the one that didn't work had a reason for it, and also it may have showed a little bit of excess power. And excess power comes very early, in fact, almost instantaneously, if you really look at it carefully. And the reason for that, the main reason I think for that, I think, is the reaction of deuterium with boron. But eventually it goes back to normal, and that reaction will stop. As far as I can tell, it's the normal loading rate. I mean, the loading curves look very similar to palladium. But why does the boron work so well? My thought is that it's oxygen-free palladium material. Like Dr. Imam said, when you make it and the boron will react with any oxygen, B2O3 is much less dense than molten palladium. It'll skim off the surface, and any oxygen then is removed from the material. And another reason for that is the Johnson-Matthey material that Palladium used that worked so well. In one of the Fleischmann letters, Martin said he gave instructions on how he wanted this made. He wanted the palladium made under cracked ammonia. Well, cracked ammonia, when it's cracked, is nitrogen and hydrogen. So the hydrogen in the atmosphere will react with oxygen in the palladium and remove it as water vapor. So that is probably also very low oxygen content. And co-deposition, I've talked to Pam and other people, and they say that palladium is deposited right out of solution and very little oxygen in the co-deposition type palladium. So that might be a key. What we need is, of course, more work on the palladium-boron, and that's what Steve Kaczynski and Dave Nagel and I and Dr. Imam are trying to do. And so more research is needed. That's where we are right now. Anyway, I guess that's my time, and thank you.
Thank you very much, Dr. Miles. Well, I can take 1 or 2 questions or comments. No? Just one? Mike?
If you had a perfect calorimeter, perfect measurement, do you think you'd still have all those spikes?
Yeah.
It seems beyond error. It's if nature follows equations, say the Hamiltonian, what you ultimately have probably is a series of nonlinear equations, and you have a chaotic condition.
Yeah. Well, those points are the average of each day. They're not instantaneous points, but I just average each day out, and that's, some days you do have more excess heat than others. And so this is a daily average that you see there on the points.
So same thing with the planetary system. You can average those, but it's still chaotic.
Yeah.
At an ultimate level.
Right.
So maybe more precision isn't going to help that much.
Yeah, sometimes the excess power stays fairly steady for maybe several hours, but also remember, I'd like to change things almost every day, like change the current, change the bath temperature, and so I was changing things as well. Mike?
Hey, I think, well, I'd like you to comment on the following thought, that the magic of boron is that it avoids the need for patience.
Right.
The effect occurs much more quickly. And some of our pure palladium cathodes have not produced excess heat until 1,000 hours into the experiment. With your palladium-boron stuff, shows up more or less straight out. And very few people had the patience to run experiments for 1,000 hours. Martin and Stan used to run them for 3 months before they'd abandon them.
Yeah, right.
So that level of patience is very, very rare in anything, actually, but particularly not in science.
Right. Yeah, okay. Yeah, I agree. Yeah.
Okay, small.
I hate to pour cold water on this, but and it's very important that we look at the palladium-boron system. I think you've essentially shown us a possible path. But what I have to say is that I have tried that path myself,
Right.
independent of samples that you supplied. These were supplied from other sources, and have failed to see not only the ability to load, but any excess energy.
Right.
So there is another variable obviously operating. And I would suggest that it's really necessary to start looking at this in a more objective way using modern equipment and information that we presently have available now that you did not have available at the time you did those other experiments, to try to figure out exactly what's going on, because there's something else besides what we think is going on.
Right. Well, palladium-boron has to be made in an exact way, and Dr. Iman made it in a certain way. For one thing, you have to reproduce exactly how he made the palladium-boron to get the same effect, I think. And also, everybody doesn't set up experiments the same as I do. You know, how you polish the electrode, what you do before the experiment, how careful you are to keep water contamination out of the system. There's a lot of variables during the preparation as well, and those have to be made the same in order to get the same results.
Okay.
Right.
The last.
Just adding a comment to what Mike had said earlier, being impatient, what we went to were thin films so that you could load quickly. And has anyone ever done a thin film type palladium-boron experiment? I don't think so. But
I don't know whether you could make thin films. Dr. Iman would know that, maybe.
can you make one?
Okay.
Okay. So let's thank all the speakers again.
Okay, thank you. You take this.